Hi, I'm Laura Matson from Sandia National Laboratories. I'll be talking about using eye movements to assess human comprehension of data visualizations. So evaluating visualizations is a really hard problem. When it's done at all, it's often done with a user study that uses a specific visualization and people doing a very specific task. But it would be really nice to have more generalizable evaluation methods that could be used iteratively during the design process. So how can we develop more useful generalizable tools for evaluating visualizations? So one way to come at this problem is to think about what do all visualizations have in common, and that is the human brain. So all visualizations are designed to convey information to a human who's doing some kind of analysis or making some decision. So if we can think about this problem from the perspective of human cognition and the commonalities and biases that arise in human visual cognition, that might get us a little bit closer to having some generalizable evaluation methods. So to get at this perennial question of what makes a data visualization effective, we can instead ask, how well does the visualization support the viewer's cognitive processing? So we know from prior literature that perceptual aspects of a visualization influence viewers' cognitive processes. So for example, changing the visual representation can change how people interpret a visualization. We also know that viewers tend to look at the most visually salient regions of a visualization. We also know that top-down factors such as task are very important. So people out in the real world might use the same type of visualization or the exact same visualization to support different tasks. We know that changing tasks changes how people look at natural scenes. So we can presume that that's the case for visualizations as well. So in this example, if you show people the exact same scene and ask them how many floors does the tallest building have versus how many cars are in the scene, you get very different patterns of eye movements. So just to spend a moment defining bottom-up and top-down visual processing, these are two parallel neural processes that guide visual processing in the brain. So bottom-up is also known as stimulus-driven visual attention, and it is captured automatically by the physical properties of the stimulus, such as color, shape, orientation, or motion. Like in these examples here, the thing that is different from the others pops out and automatically captures your attention. In contrast, top-down visual processing or visual attention, also known as goal-oriented visual attention, is allocated voluntarily according to the viewer's goals and expectations. So it's impacted by their current goal, their past experience, and their cognitive load. So I'm going to talk a little bit about each of these factors. So I'll start by talking about how assessing bottom-up visual saliency for visualizations is potentially a useful evaluation tool. Then I'll talk about assessing the impact of top-down factors, and finally give an example of an application that ties these two things together. So bottom-up visual saliency can be modeled, and there are many different computational models out there that do this. The example here is based on the Itty and Koch 2001 model, kind of a classic one. So these models, or this model in particular, takes in an image, divides it into feature maps based on things like color, intensity, and line orientation. It compares those maps across different scales to identify regions where there are changes in any of those features. And then those are combined to create the saliency map. And the saliency map is essentially a prediction based on these bottom-up features of where someone will look when they look at this image. So when we were looking at generalizable ways to evaluate data visualizations, we thought having a bottom-up saliency map could be really useful, because if you know what is most salient, what's likely to capture people's attention, you can then look at the viz design and see if the things that are most important to the viewer, the end user, are also the most salient. However, we found that many of the existing saliency models fail for abstract visualizations. So here are three examples of three pretty simple data visualizations run through three different saliency models, and they all fail pretty spectacularly to predict where people will look in these images. So we did some research to investigate why saliency models typically fail for viz. So we dug into the features of the models themselves, looking at three common saliency models. and then did some eye tracking work where we had 30 participants look at 62 different visualizations. And this was just a previewing task where people looked at each visualization for 5 seconds. So kind of simulating if you came across this viz in a newspaper or journal article and you're just trying to gather information from it, to see what people actually looked at and how that compared to the saliency models. So one kind of the most interesting thing we found in this eye tracking study was we divided the visualizations into different regions of interest. And when we did a comparison that compared regions containing text, regions containing the actual data, and other regions, such as regions with numbers or graphics and things like that, we found in 2 different studies that people spend a lot of their time looking at the text. So in our first eye tracking study, where we had visualizations with informative text, people spent 60% of their fixations looking at that text. Only about 30% of the fixations were devoted to the actual data. We did a second study where we made the text in the visualizations totally uninformative, so just things like acronyms or single letters, and still people had about 40% of their fixations devoted to looking at that uninformative text, which was almost as much as they devoted to the actual data. So one of the key reasons that saliency models fail for viz is that their feature sets are inadequate, and most importantly, they weren't accounting for attention to text. So past research on eye tracking and reading has really demonstrated that for experienced readers, text is essentially a bottom-up feature as well that automatically grabs your attention. But most saliency models don't pick it up because it's relatively small and doesn't have high contrast and things like that. We also found that the RGB color space that's used in a lot of saliency models doesn't correspond well to human color perception, so that leads to some of the errors we see. And these saliency models that were out there use inappropriate spatial scales and weighting when they're applied to viz. So they use spatial scales that work fine for natural scenes, but visualizations have features that are very small relative to the extent of the image, but still important. And when the images are resized and smoothed to go through these models, that eliminates a lot of those fine details. And finally, the saliency models often incorporate a center bias that doesn't hold for visualizations. So we developed what we call the data visualization saliency model to address some of these issues with the existing saliency models. We have a paper from 2017 that shows that the DVS model provides significantly better match to human fixation data than prior saliency models. So in addition to modifying some of the features in the classic IDI model, we added a text saliency map that accounts for all the attention that people pay to text and visualizations. We have a weighted sum of those 2 maps to create the DVS saliency map. And the code for this model is available here at this URL in MATLAB if you'd like to use it yourself. So here's an example of the DVS model's predictions versus actual human fixations to some visualizations, and it's a pretty good match. It's not perfect. DVS over predicts how much people will look at numbers, which we found in our eye tracking studies. People don't tend to look at those at all. In some cases, it overcompensates for the center bias. There are some cases where people have a center bias for viz as well, which the DVS model does not have. But overall, it does a pretty good job. So now that we have a pretty good bottom-up saliency map to make predictions about where people will look in visualizations, we also need to consider the impact of top-down factors. So not many studies have investigated the impact of task on patterns of attention and visualizations. Some of the studies out there look at this from the perspective of which task is the best fit or which visualization is the best fit for a particular task. But there hasn't been that much of using a single visual representation and looking at how different tasks change how people look at that visualization. So we did a really simple study to give an example of this. So we looked at the impact of task on viewing patterns for scatter plots. So we had 30 participants who looked at 32 scatter plots each. The scatter plots had 8 different types of trends and either 2 or 4 outliers in each one. For half of them, the participants described the trend, and for half, they described the outliers. and this was counterbalanced. So for each visual stimulus, half the participants did the trend task, half did the outlier task. Participants looked at each plot for up to 10 seconds and then provided a verbal description of either the trend or the outliers, depending on which block they were on. Once again, we divided the scatter plots into regions of interest so we could analyze patterns of eye movements. In general, we found that participants had more and shorter fixations in the outlier task than in the trend task. So this is a pattern that's indicative of visual search. And most importantly, we found that in the outlier task, these darker gray bars, people had a higher proportion of fixations to the outliers. In the trend task, with lighter gray bars here, people had a higher proportion of fixations to the trend. So just to give a couple little examples, the outliers are indicated there with arrows. But you can see in the trend task, participants tended to look at the title, the axes, and the trend, whereas in the outlier task, they looked at the outliers. Here's just another example of the same thing. We see this pattern over and over again. So yes, the task does impact patterns of eye movements for data visualizations. So this just kind of drives home the fact that we need to take bottom-up and top-down factors into account when evaluating data visualizations. Assessing the visual saliency can be really useful, but combining it with an assessment of common patterns of attention for particular tasks is even better. So the Viz community has a lot of taxonomies that have been developed to describe the different types of tasks that people do with different types of visualizations. So that can be a really nice starting point, I think, for future research on the impact of task on visual attention in data viz. So finally, just to wrap up with an example of an application where we tie these two things together. So this example has to do with synthetic aperture radar, or SAR. This is a type of radar that is processed into images that they look kind of like a black and white aerial image. And analysts process this data to look for certain kinds of targets. So in SAR, the same kind of image or the same scene can be imaged repeatedly over extended periods of time, allowing the analyst to see changes. So this is an example of what's called the coherent change detection product. And over time, we can see that in this scene, some cars drove down a dirt road and left some ruts in the mud. And so we can see that change in the SAR images. So we wanted to know what features of the SAR and CCD images support an imagery analyst task. So first, what are the most visually salient features, and are those the most important ones? And second, what are the most task-relevant features? And as a secondary question, we wanted to know if task performance was different for more experienced or less experienced analysts. So we collected eye tracking data from experienced and inexperienced viewers and took those gaze patterns and compared them to visual saliency maps to see how they differed. So in this task, we had a target detection task using two images presented side by side. We had the SAR magnitude image on the left, coherent change detection image on the right, and we had three groups of participants. So professional SAR analysts, SAR engineers who design these systems and are very familiar with the imagery but are not analysts, and then novices who had only just been trained on how to read SAR images. So here's an example of where an expert SAR analyst looked at one of our images. This red box shows where the change is. That's the target of interest. Here's one of the SAR engineers. That person also looks and detects the change right away, the change of interest, but they look back and forth to the raw SAR magnitude image a few times to get the context for understanding this change. Our novice didn't really look at the target at all. So we had 8 participants in each group, and if we look at the heat maps for all of their eye tracking data, we see similar patterns for all of those participants. So now that we have our eye tracking gaze maps, we can compare those to saliency maps of these images. So we calculated the percentage of saliency in the regions of interest around our targets, and we compared that to the percentage of fixations, the percentage of gaze in each of those regions of interest. And what we found was that across all of our stimuli, for the novices here in green and the knowledgeable non-analysts in blue, we see a significant correlation between the percentage of saliency in the ROI and the percentage of gaze to that ROI. For the imagery analysts, the professional analysts, we don't see any correlation at all. So the professionals are effectively ignoring things that are highly salient but not task relevant. So we can apply these results in several different ways. So first of all, we use this information to improve the training of new analysts by gaining a better understanding of what visual features the experienced analysts actually use. We can also change the images themselves by modulating the visual saliency of features that are task relevant versus task irrelevant. And finally, we can use the eye tracking data to help tune automatic feature detection algorithms so that they're using parameters that are similar to what the expert analysts are using when they make their decisions. Because we want the outputs of any new automated analyses to help the analysts and keep their high level of performance and not hinder them or confuse them in any way. So just to summarize, having bottom-up saliency maps can be a really useful tool for evaluating data visualizations, especially in a qualitative sort of way, because you can look at what's salient from a bottom-up perspective, what will be most likely to draw people's attention, and then figure out if that is actually the most important or most task-relevant information in the visualization. And if not, it might be worthwhile to change up the design. Eye tracking can provide a much richer data set on top of that, because by looking at the differences between what's salient and the eye tracking data can reveal top-down factors that impact attention, such as differences in task or differences due to different levels of experience of the viewer. So combining these two factors, getting at both aspects of visual attention, can be really useful for both evaluating data visualizations and just advancing our understanding of visualization cognition. So there's a lot more work to be done in this field. I think it's a very interesting emerging topic. There's a lot of opportunities for people who do eye tracking to get in on the research on data visualizations and visual cognition. So thank you very much.